Good day, everyone. So we'll be discussing titration today. So specifically on acid-base titration, and for sure you are familiar with some of these common acids and bases that we see even in the market or at home. So we see some examples of this. So for today, these are our objectives. We will identify strong, weak acids and bases. Write the net ion equation for a titration reaction. So we'll define some terms related to titration, differentiate between equivalence point and endpoint, and identify the stages or regions in a titration process. And also explain the importance of the skill in performing an acid-base titration and perform calculations involving molarity and number or moles in relation to titration. So we start off, for sure you are familiar with some of the natural sources of acids. Something that is sour, we associate it as an acid, no? Like some of the fruits, they contain citric acid, example in lemons, in sour milk, in grapefruit. So these are some of the natural acids. So we associate something that is being sour is actually an acid. So some common acids we have here and bases. And remember in our Gen Chem, so these acids and bases, so they are classified as strong or weak acid or base. So for example, your nitric acid, that is a strong acid, and then your sulfuric acid, so that is a strong acid as well, HCl. Um, an example of a weak acid is the THP. And then for the bases, strong bases commonly are sodium hydroxide, barium hydroxide, KOH, and the carbonate is a weak base. So for sure, you've learned this in your senior high school about strong acid, weak acid, the same thing with the base, strong base, and weak base. So basically, the reason is in the association, in the dissociation or ionization of these acids and bases when they react with each other or when they react with water. So for example, we look at the reaction in number 1 between strong base and strong acid. And in number 2, we have strong acid and strong base. And then number 3, weak acid versus strong base. So we'll cover basically these 3 types of reactions in this unit. So as what I've said, in your Gen Chem in senior high school, so you classify these acids or bases according to strong or weak. So if it's a strong, it means that your acid or base completely dissociates into ions. So just like in reaction number 1. So after some time, you don't have the sodium hydroxide and nitric acid anymore. So everything is converted into products. The same thing, no? In the second reaction, it's also between strong acid, between strong. But this time strong acid with a strong base. So both completely dissociated into ions. But in the third equation, so this is a reaction between weak acid and strong base. So typically, this is an example of a partial dissociation, meaning not all of the acetic acid that you see here, so not all of the acetic acid is actually converted into products. So actually there's a certain fraction that is converted into products, and there's also a certain fraction that would remain undissociated. That's why it's called weak acid. Okay, so the technique is actually a volumetric analysis. We call as titration. So this is the considered the heart of titration. So it would involve titration. So titration is the controlled addition and measurement of the amount of a solution of known concentration, which we call as the titrant, that is required to completely react with a measured amount of a solution of a known concentration, which is the analyte. So in other words, the keywords here, analyte, meaning that's our unknown solution. We would like to know something about our analyte. We would like to know the concentration of substance of interest in the analyte. by reacting it with our titrant. So the titrant is the standard solution, meaning the solution of known concentration. So titration or acid-base reaction is also called neutralization. Basically, the reaction when acid and base react, so the products are salt and then water. Okay, this is a typical setup of a titration process. So usually we have here the burette. This is where we place our titrant, and then our sample is in the flask, usually a linear flask or any flask. So this will place our sample or unknown solution, the analyte. Of course, we clamp the burette using the burette stand, the iron stand. So this is, then we also use a magnetic stirrer. So you don't have to swirl it manually. But if you don't have the magnetic stirrer, so of course you'll be required to swirl the solution manually. Okay. So since our acid and bases are actually colorless, many, no, or most of these are actually colorless. So we will be using an indicator to tell us that the reaction between these two is already completed. Okay, so you would know that we have this equivalence point because remember, titration is actually a solution stoichiometry. So it's the two, the titrant and the analyte, or the acid and the base, are reacting according to the balance equation. So what happens, remember, we gradually add the titrant until all of our analyte in our unknown solution has reacted to our added titrant. But how do we determine that? Again, as what we said earlier, we add an indicator to tell us that the reaction is completed. So the point in which the two amounts are stoichiometrically equal, that's what we call as the equivalence point. And we do not observe this in the titration process. Instead, we'll be observing, what we will observe is the endpoint. But theoretically, the equivalence point is the point at which the two solutions used in titration are actually present in chemically equivalent amounts or stoichiometrically equal. So we can also monitor the pH at any point of the titration using a pH meter. Okay, so what we can observe is what we call as the endpoint. This is when we add one drop in excess of our titrant, because at the equivalence point, so there's no change of color. But the moment you add a titrant, one drop in excess, that's when it changes color. So the usual indicator, actually it's a weak organic acid, and it has a different color relative to its conjugate base. So we can use a specific indicator according to the type of titration that we will actually perform. So this is the relationship between the weak acid, and the ratio of the two forms is basically dependent on the amount of the hydronium concentration. This one. Okay. So indicators change color at different pH values. So depending on the type of titration, so we carefully choose our indicator for a certain type of titration. So it should be chosen carefully so that the endpoint is actually close to the equivalence point. So that's the basis in choosing the indicator. These are some typical examples of these indicators, and look at the changes in the colors at different pH. So when we monitor our titration, the progress of titration, so we can actually describe using what we call as the titration curve. So this is a plot simply of the pH of our analyte and the volume of the titrant that is added. So let's start with the first type. So this is between a strong acid and a strong base. So remember, when the strong acid and the strong base the net ion equation for this is simply the formation of water, H plus and then OH minus forming water. So what we do is we apply the concept of stoichiometry, we'll apply the concept of limiting and excess reactant in this topic. So to calculate the pH, we need to know the H plus at any given time, and we divide it by the total volume of okay, total volume of the solution. So pH is equal to negative log of H plus. So this is our equation, the complete and balanced equation, and then this one is our net ionic equation. So at the equivalence point, the pH actually here is 7. So remember, this is stoichiometry, meaning at the equivalence point, the amount of the acid is stoichiometrically equal to the amount of your base. So you know the formula that we usually use, the molarity acid times volume of the acid, plus remember the mole ratio or stoichiometric ratio between the acid and the base. So we simply use basic solution stoichiometry. So this is the titration curve of a typical strong acid, strong base. So if you look at the figures, so we have different regions. So we have the region before the equivalence point, and then we have the region at the equivalence point, and then the region after the equivalence point. So when we calculate for the pH, so we actually have here a strategy in how to calculate. So before the equivalence point, so we'll just consider it as a strong acid, and then at equivalence point, it's simply water, the solvent, and after that is a strong base. In other words, in this column, this will tell us the limiting reactant. So the limiting, or this will tell us, and this will tell us to use the concept of the limiting and then the excess. So we'll illustrate that in a while. Okay, so we have this problem. So consider the titration of a 50 ml of 0.2 molar nitric acid with 0.100 molar zinc hydroxide. So calculate the pH at various points and then construct a titration curve. So we have volumes of titrant added at 0, 10, 20, 50, 100, and then 150. Okay, so at the start, meaning at pre-equivalence point, so meaning at the start, in other words, no titrant is added yet. So what we have is just an acid. So nitric acid is actually a strong acid. So whatever the value of our nitric acid, so that's also the, whatever the molarity of the nitric acid, that's also the molarity of our H plus. Okay. So in here, at the pre-equivalence point, our pH is basically 0.7. So just get directly the negative log of the 0.2 molar of the nitric acid. So that's 0.7. And then next is when we add 10 ml of our titrant, of our zinc hydroxide. So we'll use stoichiometry. Which one is the limiting, which one is in excess. So it will tell us how to calculate and go about solving the pH. So this is just a simple stoichiometry table. So before adding, so the total, you can actually work with millimoles so that you don't have to convert ml into liter. Remember, molarity is moles per liter. So you can also use millimoles per ml. So it's also molarity. So we don't need to convert the ml to liter. So initially, so the number of moles of our acid from nitric acid, that is 50 ml times 0.2, that's around 10 millimole. And our base that we have added is 10 ml times 0.1, it's 1 millimole. So the ratio is 10 of our acid millimole and 1 millimole for our base. Remember the stoichiometric ratio between sodium hydroxide and H plus is 1:1. So obviously here the excess reactant is our acid. So we have 9 millimoles. So the excess, so it will, because the all of our base is neutralized by the acid and by some of the acid, and it has an excess amount which is 9 millimoles. So the remaining acid that is not that was not used to neutralize our hydroxide is 9 millimoles. So we get its concentration. So we divide the total volume. It's now 50 from the original plus the 10 ml of the added sodium hydroxide. So that's 60. So 9 over 60. So that's 0.150 molar. So that will give us a pH of 0.8. Next is when we add 20 ml sodium hydroxide, the same process, the same way. So we get the stoichiometry. Our excess is still the nitric acid. It's excess by 8 millimole. So all of the hydroxide that we have, which is 2.0 millimole, is all of the hydroxide is neutralized by also 2 millimoles of H plus. So what remains after neutralization, meaning the excess amount of H plus, is 8 millimole. Then we divide the total volume, which is already 70 because we added 20 ml. So 8 over 70 gives us 0.114 molar. That gives us the pH value of 0.9. Okay, and then at 50 ml, same process. So the excess reactant here is still the H plus. Okay, so the concentration is 0.05 and the pH here is 1.3. So when we add 100 ml of sodium hydroxide, this is when we attain the equivalence point, because you look at the value. So the amount of the acid and the base, the two amounts are just stoichiometrically equal, meaning there's no limiting, there's no excess. It's simply water. No? So the product is simply the water, and we know water is pH is actually 7. And then after the equivalence point, so this is when we have 150 ml of sodium hydroxide. So it's now the reverse. So before the equivalence point, the acid is our excess. After the equivalence point, it is the base now that is our excess, our agent. So example, when we add 150 ml, so we have an excess of 5 millimole of our base. So that gives us the hydroxide concentration of 0.025. So you can calculate pOH. So we get 1.6. So we can get a pH. So remember, pH and pOH is actually equal to 14. So we just subtract 14. We just subtract pOH from the 14. So we get the pH of around 12.4. Here. So this is the summary of the pH. So gradually it increases, and then there's a steep increase in the pH. So this is the overall look of the titration curve. So basically the pH starts out very low, so gradually it increases as we add our base, and suddenly the pH rises steeply at the vicinity of our equivalence point, which is actually at around pH is equal to 7. And there are many indicators that we can use within this range. So beyond this very steep portion, the pH increases slowly as more base is actually added. So we started at the pH value of very low, and then gradually increasing, and then it's suddenly it increases steeply, and then it gives us the pH at basic values and it also increase but gradually. Okay, so the other combination is when we have weak acid and strong base. So these are some of the strategies that we can use in solving the pH at certain point of the titration process. And then also weak acid and strong base. So this is also the strategy that you can use in solving. We will have a sample calculations on this remaining two in the next part. So some of the major differences between strong acid, strong base, and weak acid, strong base titration curve. Basically, the initial pH is higher because we are starting with in the strong acids, it's very strong, so the pH will be very low. And of course, the weak acid, the pH we expect it's much higher. Okay, so strong acids have very low pH. So between strong acid and weak acid, so the weak acid has higher pH. So the initial pH is higher for weak acid, strong base titration curve. Gradually rising portion of the curve, there is a buffer region that we call that would appear before the steep rise towards the equivalence point. So there's a buffer region. So we'll explain this in the second part. And then the equivalence point compared to the strong acid strong base, which is actually 7. For weak acid strong base titration curve, the equivalence point is actually above 7. So it's a basic region. And in the steep rise interval is actually less pronounced. If you look at the strong acid strong base, it's very steep, almost a straight line. But our weak acid strong base, it's quite different. So it's gradually increasing. There's certain region we call as the buffer region. The same thing with the weak base and strong acid titration curves. So initially the pH, the difference is just the reverse. So we actually start with pH above 7, and then we have the buffer region, gradually decreases portion of the curve, and then the steep fall towards the equivalence point, and the pH at equivalence point is actually less than 7. But this is when the titrant, the strong acid, is now in excess. And then pH decrease slowly as excess strong acid is added. So basically that's the difference between weak base strong acid titration curve and the weak acid strong base titration curve. So you would know because the pH at the start. For weak base strong acid titration curve. So initially, since it's actually a weak base, so being titrated with a strong acid, so the weak base, the pH is above 7. But weak acid, so when it's titrated with a strong base, so initially the pH is below 7.